Hey, welcome to another video. So in this lesson, we're going to talk about how to use the properties of logarithms to expand logarithms. Now, why in the world would we want to do that? Well, when we get to calculus 1, maybe calculus 2, depends on when you get derivatives of logarithms, it really helps to be able to expand logarithms and to take a derivative after you've expanded them. So when you get there, you're like, oh, that makes sense. For now, sometimes we expand them, we're solving equations. We need to do that once in a while. Sometimes it puts them in a better format for us. So a few reasons why we want to do it. Honestly, in this video, we're just practicing this. So we're going to be using these properties to take logarithms that have multiplication, division, or exponents and expand them. Make, honestly, as many logarithms as possible using these to get these. That's the idea. Separating multiplication into addition of two logarithms, division into subtraction of two logarithms with the same base, and using that power property to move that exponent as a coefficient. In the next video, we'll go backwards. We'll take logarithms that are added or subtracted or have a coefficient and change them into more condensed versions of the same thing. They do mean the same thing. We're just using properties to show them a little bit differently because it benefits us on certain occasions. So let's get right to it. Here's the process, what I would want you to go through. Whenever you have to expand a logarithm, number one, take a look at your logarithm. Make sure a couple things have happened. Firstly, make sure everything's factored. So if you have an expression like we see in a couple of, well, this one, where we can factor this. We want to make sure that's done first because when we're expanding logarithms, we want it fully expanded, and anything that has a product needs to get expanded, or a quotient needs to get expanded. Also, because radicals really can be represented by exponents that are fractions, we're going to write all of our radicals as exponents. And finally, we're going to show any sort of product that there is. We're going to explicitly show with a little dot that certain things are being multiplied together so we know to expand them. So let's take a look at what I mean in this example. What we're going to do first, we're going to take a look at this. This is a logarithm. Oh, the base should be e. We know it's e. We're going to take a look at first factoring. So is everything factored? We know that it is. Is it necessary to write this in x first and then factor out a negative? You can. It's not super necessary for what we're doing. Some occasions would call for it. So we're not going to do that. So everything is considered factored. The next thing we're going to do, we're going to write that radical as a 1/2 power because that is a square root. We're also going to explicitly show that there is a product here. Now here's the order in which you undo or expand these logarithms. I can't say you always separate products first. You always move your exponent to the front first. I can't say that because it really depends. Here's how to know what to do first. This is not in a textbook. You just have to look at it and figure it out. Here it is. What operation is connecting the entire argument of your logarithm? What's holding it together at this moment? Is it an exponent? Is that exponent holding all this together? Or is it the product? There's only two things going on. There's a couple exponents and there's a product here. So we factor, okay, it's factored. We make sure our radical is written as an exponent if we have one. We show products and or quotients everywhere we can, and then we look and see what operation is connecting this thing. Right now, what's holding all of this together is that product. There's no quotient, but that exponent is not applied to the entire argument. Neither is this one. So it's got to be the product that's holding together. Separate that first. So we look over here. How do we separate products? Well, we know that we can make two logarithms that are added together with the same base. Since our base is e, we're going to write ln. And we know that logarithms are added together when we expand our multiplication or our product within the argument of our logarithm. And then we do the same exact thing. We take a look at this. Now, these should be factored, of course, and all of our radicals are still written as exponents. That's only done one time, then we're good for the rest of our expansion here. But then we consider what is holding this together. What is holding that argument together? Is there anything I can expand? Is there a product, a quotient, or an exponent? That's only three that we really look for. Well, there's an exponent, and that is on top of all of this argument, if you will, or applied to the entire argument. That's something we can expand. So we look down at our power property and we understand that any sort of an exponent can be written as a coefficient. So we're going to move that too. Likewise, This argument, or this factor, I suppose, has a 1/2 power applied to all of it. So we can move that. That's an exponent. We can move it as a coefficient. And we're done expanding. Now you might ask, well, what about that one? Can't you expand that? No, you can't. The only things in logarithms you can actually expand into additional logarithms or moving exponents to the front is with these three properties. There's no way to expand subtraction or by addition. So if we had to see a minus or a plus, you're done. Do we have to put parentheses here? Yes, absolutely. We need to show that logarithm has a 1 minus x as its argument. We can't miss that because otherwise it's very confusing. If we did ln of 1 minus x, that would be 0 times 1/2 minus x. We want to make sure that we understand that's the thing that's inside that logarithm. So this is as much as we can do. We've looked at it, we've made sure it's factored, our radicals are exponents. We then look at what is connecting the entire argument. We separate that one piece. And then we continue to look inside each argument and say, what's connecting this one? Okay, an exponent. What's connecting this one? Okay, an exponent's on top of all that. And we start undoing as much as we can. When we get down to the point where we have individual factors, individual term factors, or factors that have more than one term in them, you're done. That's as far as we can go. Let's take a look at the next example. So the first thing we're understanding is that this is a logarithm. It's got a base of 5, and wow, there's a lot going on in here. Number one thing in your head is when you see expansion of logarithms, I need you to factor stuff. So this is factored. X squared plus 1, you can't go anymore. That's an irreducible quadratic. We've seen it many times. But x squared minus 1 is certainly factorable, and we need to factor that right away. The other thing we're going to do is every single time we see a radical, we're going to write that as an exponent. That allows us to notice in our power property, usually at the end here, that we can move that as a coefficient. So we've looked, we said, yep, factor x minus 1, x plus 1. We know that that was written to power 1/2, but it's x squared plus 1. That entire thing is inside that radical. That's an inside parentheses, and it has that exponent to it. Now what we do is the most important part. We look and see how this argument is connected. So what is joining this together? Is it an exponent or is it multiplication and division? So we're going to show as much as we can. We know that this is division. That's pretty good. We know that because it's already shown, we know that that's multiplication, and we know that that exponent is connecting just to this numerator. So the thing that's joining this is multiplication and division. The overarching operators here are multiplication, division. We're going to undo those first. Notice how the exponent is not applied to everything. If it was, that would be the first thing we're doing, but it's not here. It's just being applied to the numerator. Multiplication, division is connecting the rest of the stuff. So we're going to expand that first. Now, listen real carefully. You can do all of this at once if you follow a very simple principle. Things, or factors, on the numerator are positive or added logarithms, and things on the denominator are subtracted logarithms. Those factors on the denominator create subtracted logarithms. That's really important because what happens is sometimes when we try to do this in multiple steps, it gets way confusing and we start making sign errors. So I've seen it from time to time where teachers or textbooks will say, okay, now first thing you do is take this, subtract a logarithm of both those terms. Well, because those terms are multiplied, you would show addition, and then you'd have to distribute a negative through. That's much more confusing than what I'm about to show you here. So what I'm going to show you is look at all your factors that are connected by multiplication and division. The factors on the numerator are going to get positive logarithms to start and added for every factor that's on the numerator. On the denominator, we're going to subtract logarithms that contain each of those factors. So what that looks like here is we're going to start with our numerator factors. We're going to go, okay, well, we're going to have a log base 5. And we're going to take the first numerator factor that we see. Well, there's only one of them. There's x squared plus 1. It's an irreducible quadratic raised to the 1/3 power. So that's a positive logarithm. That's great. Now, since we've exhausted all of the factors on our numerator, we're going to look at the factors on the denominator. But we're going to understand something very important. every one of those factors that's on the denominator is going to create a subtraction of a logarithm. It's going to do this for every factor that's down here. So if we want to extend this a little bit, let's say that this also had maybe a k. We would have log base a of m minus log base a of n minus log base a of k. You subtract a logarithm for every one of those factors, and the reason that that would happen is because if you did it a different way, I'm going to kind of show this down here. If you showed it this way, and you did log base a of m minus log base a of n times k, well, you could separate that by addition, but that would be inside this big bracket, and that minus would eventually distribute. I hope you see that. I'm going to show that here in just a moment that that's true. So let's continue. Now that we have these all factored up and we know what our numerator and denominator factors are, all our numerator is positive, now we're going to subtract for each factor. So log base 5 of x minus 1, that's one factor on the denominator, minus log base 5 of x plus 1. We are almost done. The last thing that we've got to do is reevaluate all of our logarithms and see if we can expand them further. So log base 5 of x plus 1, you cannot expand addition. Minus 1, you cannot expand subtraction. There's no exponent holding any of those arguments together. This exponent does need to move to as a coefficient when we're expanding. So we want to undo as much as possible using these properties. So we're going to take that, write this as 1/3, and then a log base 5 of x squared plus 1. We need parentheses, and we need parentheses on every one of those arguments. That's as expanded as we can get. Now, I did say that I would show you a slightly different way as I mentioned this. If you want to understand a little bit more about why we're subtracting a logarithm with each of these factors on the denominator, and you didn't quite follow what I said, I can show you right here explicitly. What would happen is that if you were to subtract numerator minus log containing denominator, looks like that. And if we further understand that, well, because that's a product, we can expand that as well via two logarithms being added. Now this is obviously different from this, and that's a problem. And here's why it's a problem. When you subtract this logarithm, well, you're subtracting everything that becomes as well. So really what we would have is this bracket around that. And by subtracting each one of those terms, you end up getting this exact thing. And this is why I teach it the way that I do. Just look at the factors on the denominator and subtract logarithms containing each of them. Because that puts all of this in summary and lets you kind of make a shortcut instead of having to show a bracket and then a distribution, when in fact you can get the same thing by understanding what's really happening. You're just subtracting logarithms that contain the factors on the denominator, and you're adding logarithms that contain the factors on the numerator. That's really all there is to it. We're going to come back and we're going to do that one. I'll show you something quite similar. All right, let's go ahead and do one more. So we're taking a look at this. We know we want to factor everything. It is factored. We have x plus 1, x minus 2, quantity squared, and x minus 1. Nothing can be additionally factored. But what we are going to do is write this radical as a 1/2 power, and then we're going to show all the products and quotients if they're not already shown. So we have a product here and here. The quotient we can clearly see. So then we look, and this is the most important part, just look at the operations that are connecting this argument. Because these exponents are just on these individual factors, it's multiplication and division that's holding this together. Well, we're going to separate that first. Every factor on the numerator is going to create positive logs or logs that are added together. Every factor in the denominator, we're going to separate those by subtracted logarithms. So log of x cubed plus log of x plus 1 to the 1/2. And then minus these factors. Inside these logarithms. So log of x minus 2 to the second power, and then minus log of x minus 1. So since that's all done in one step, there's really only one more thing we need to do. We reevaluate each of these logarithms and look to see if they have anything else holding that argument together that can be expanded. In these cases, just a few exponents. So x minus 1 is factored, you cannot expand subtraction. X minus 2 to the second power, we can move that 2. This 1/2, yeah, we can't move that to the front as a coefficient, and so can the 3. And so we moved all of them. We have that 3 as a coefficient, the 1/2 as a coefficient, the 2 as a coefficient, and that looks pretty good. This is as far as we can go. So this is what we would call fully expanded. Every product and every quotient has been expanded as addition and subtraction respectively, and all of our exponents has been moved as coefficients. I hope it's making sense to you. I hope you're seeing it's not really that big of a deal, not really that hard, as long as we're following these properties that I've given to you. Again, the main thing is write out factored versions of your expression. Once you've done that, make sure that all radicals are written as exponents. Then look at what is connecting your argument. Usually it's products and quotients, which we can expand all at one time. Factors on the numerator create positive logarithms or ones being added. Factors on the denominator create negative logarithms or ones being subtracted. Usually I deal with the numerator factors first and then the denominator factors. After that, we move our exponents as coefficients and then we're done. All right, let's go through 2 more examples quite quickly. So in the first one, we're taking a look at that as a natural logarithm, so it is a log. We're going to firstly make sure everything's factored. It looks like it's factored just fine. We're going to change every one of those radicals, which is only one of them, into a 1/3 power in this case, and then show our products between there. The reason why we're doing this example is we can't forget that 4 and 5 are actually factors, and they do need to be expanded. Even though they're constant factors, they do need to be shown as ln of 5 and ln of 4 somewhere. So we're going to show that. So we've got 5 times x squared times 7 minus 2x, and that's being raised to the 1/3 power. All over, I'm going to show this explicitly 4 times x plus 1 squared. So what that lets me do, that says that we've got really 1, 2, 3, 4, 5 different factors. Some of them have exponents, but they're all connected by multiplication and or division. So I've shown that it's all factored. I've moved this as a radical into a rational exponent. I've shown my multiplication. So what we're going to do is understand that because this argument's connected by multiplication division, I'm going to choose to expand that first. I really don't want to be dealing with those exponents because they're not applied to all the factors. That has to come later with individual logarithms that are being added or subtracted in this case. So every factor that's on the numerator, all 1, 2, 3 of them, I'm going to write that as a positive ln 5 and then plus a ln for every one of those factors. So ln 5 and then plus ln x squared and then plus ln of 7 minus 2x to the 1/3. Well, that was all divided by 2 factors here, 4 and x plus 1 squared. So for every factor that's on the denominator, I'm going to subtract a logarithm containing that factor. So all numerator, 1, 2, 3, became logarithms with each of those factors inside and then added or positive, and each of the factors on the denominator created logarithms with those particular factors but being subtracted. And now we're going to take a look at it, see if anything else is connecting each of these logarithms. This is fully expanded. You can't do anything more with that. But this has an exponent. We can move that to the front as a coefficient. So does this one, and so does that one. This you can't expand. We're done. That's as much as we can expand out of this logarithm. That's a lot of them. That's, what, 5 different logarithms. There's no more exponents. That's really nice because that means that things that we do with this are a little bit easier when you don't have to deal with a cube root. Instead, that's just a 1/3 as a coefficient. That's nicer to deal with in a lot of cases. Also, don't expand pluses. Please don't do that. Or minuses. You can't do that. We've done as much as possible to expand this particular logarithm, and that's it. Also, the order of our factors doesn't really matter as long as the signs go with the appropriate factors from where they came from. So denominator factors need to have negative logarithms. Numerator factors need to have positive logarithms. And that's what we need to just understand out of taking this and expanding it as fully as possible. I hope that I'm making sense to you. I hope that you're understanding that the idea is just following those rules that we've shown and looking at what is connecting the argument of your logarithm, expanding that first. All right, last one for now. Well, this is a little bit different, isn't it? Because we've got that 2/3 power that's on the entire argument of that logarithm, base 10 logarithm, and it's not factored. So when we approach these things and we need to expand this for whatever reason you're asked to, number one thing to do, factor everything first. That is true all the time for these logarithms when we're trying to expand them. So don't do anything without factoring first. So we're going to do that. We're going to factor x squared minus 9. We're going to check that x minus 4 is factored, and it is. We don't have any radicals explicitly written, but I do want you to notice something. Do you notice that a 2/3 power is a radical? I could have given this to you as a really big cube root of all this junk squared. Now, that'd be pretty nasty of me to do that, but I could have done that. And then you would have written this as, instead of a cube root, as that 2/3 power. So I've given it to you like this, but that is possible. Now, at this point, you have an option. Before you get to the option, I do want to say something. If possible, you can simplify these. So if this had been x minus 3, you could have simplified this before you expand it. Now we have a domain issue there, but we have domain issues here anyway. So that would be something that is possible to do. So check in your logarithms to see if you can simplify your factors. That's possible, legal, and you should do it. So here we can't simplify, but we certainly could have checked that after you factor. Or later on when we're combining logarithms, what you combine can be simplified some of the times. So now that we've done that, you have options. Here are your options. Number one option, you can look at this as one expression that's raised to the 2/3 power. Because this, and here's the key, you gotta look at what's connecting the entire thing. Because this is over all of this argument, you can move this to the front of your logarithm first and be fine. That's true, you can do that. In fact, I'm gonna do that, that's option one. Option two is, because exponents distribute across multiplication and division, you can apply that exponent to every one of those factors. Okay, if you do that, then multiplication and division would now be connecting your logarithm, and you can separate by addition and subtraction, and then move your exponents later. Either one works. I can show you both. So I'm going to do option one first. Let's move that as a coefficient. Now, because we've moved the exponent that's no longer there, the rest of this logarithm is connected by multiplication and division, which we're going to separate by addition and subtraction of respective logarithms depending on where they came from the numerator denominator. So log of x minus 4 squared minus a log for each of these factors. However, I'm hoping you see it. There's something missing here. You see, when we have that 2/3 in front of this logarithm and we expand the logarithm, much like the minus in front of a logarithm that we're expanding, it's going to distribute. And so we show that because all of this junk came from that logarithm, that 2/3 also goes to all that junk. So we're going to do that, but we're going to fully expand before we do that. So that's done. We can't factor it. You can't separate it. That's done. You can't factor it. You can't separate it. There's no exponent. This you can't factor it or separate it, but you can move that exponent to the front as a coefficient. And lastly, we can distribute that 2/3. So 2/3 times 2 is 4/3, and everything else gets a minus 2/3 and a minus 2/3. That's what we call fully expanded. So there's nothing else that we can possibly break up. Everything's been distributed. There's no exponents, there's no multiplication, no division inside of any of those logarithms. This is what we mean by expanding logarithms. So I'm going to show you the different way here and say, well, what if you want to distribute that through first? Would you get anything different? No, and some people prefer it. So I wanted to give you both, to give you options. The main point is look at what is connecting the whole logarithm and deal with that first. Whether you have to distribute the exponent or move it to the front, that's fine, but you have to deal with that first. So let's take a look at what if I were to distribute that. Well, because exponents raised to exponents is multiplication, you would get a log of x minus 4 to the 4/3 over x minus 3 and x plus 3 both to the 2/3, because 1 times 2/3 in both cases is 2/3. You might be able to see right now that we're going to get exactly the same thing. You see, now that we've distributed that, everything's connected by multiplication and division. We would show our multiplication whenever you have it. And every one of the factors on the numerator is going to create a positive or added logarithm. All the factors on the denominator create a subtracted or negative logarithm. So we have positive and then subtract for those factors on the denominator, and then we're going to move our exponents. That's about it. That's fully expanded, just like what we thought we would get. It doesn't matter which order you go. Again, the idea is factor everything, make sure your radicals are exponents, and look at what is connecting your logarithm. Just deal with that first somehow, whether it's an exponent you want to distribute or move to the front, or multiplication division where we want to separate that into addition and subtraction of respective logarithms. I hope this makes sense to you. Very useful for a lot of things that we do in math. I'm going to come back with another video on how to combine. So basically going opposite of what we just done.